So we have just looked at a story and have very easily said that if there is a community having a high density, probably and a piece of idea traveling through this network cannot enter this community. We intuitively know this, but now let us try to look at it mathematically, and it is actually very easy. So to prove it mathematically, let us first refine our scenario and revise our definitions. Let us refine our scenario. So our scenario was, we had this class, right? Previously we looked at just two communities. We said that this class where people are deciding whether to be in library or whether to be outside, and then we looked at just two communities. What we do now is, let's make this a little bit more detailed. Instead of just having two communities, let's have a lot of small clusters in this entire network. So here is this class and people have made small clusters. It's actually what generally happens. A class is generally not split in two halves. People have their own bunch of friends, and if it's a class of 100 people, everybody has some bunch of 6 or 7 friends, and people exist in small clusters. And now the question which we ask is, in this class there are these two people somewhere in some part of this network who decide to go outside and have fun. And the question which we are asking is, will this idea of going outside, this decision of going outside and having fun quickly sweep the entire class? Or will here be a bunch of people, one cluster, who despite whatever will not be able to convince to go outside? So despite all of the rest class, despite the complete of the rest class is going outside, these people stay together and say that we are not going outside, and hence this diffusion process, so we call it a cascade. Whenever an idea or information diffuses, this the trajectory of this diffusion we call it a cascade as shown in the figure. So we look at whether it becomes a complete cascade or not, simply whether everybody in the class will decide to go outside and have fun, or this bunch of people will not be convinced. So this actually used to happen in our BTech class, where it was not about sitting in library or going outside, it was about whether to have a bunk or not. So whether to have a bunk or not, and then there were 3 girls in the class whose friendship was really strong, and they would always say that no, we are not going to go for bunk, and the entire class had to cancel their decision. So keeping this example apart just for fun, our question was whether this will be a complete cascade or not. So for looking at it, let's revise our definitions. So we have previously seen that if we look at one node, one person in this class, this person decides whether to go to library or whether to go outside based on the payoff functions and the number of friends. So we have there come up with a value called threshold, and we have looked at if the fraction of this person's friends who are going outside exceeds this threshold, this person will also go outside. So it was it is 40%, let's say. So it means that if 40% or more of my friends are going outside and having fun, I also go outside and have fun. And if 60% of my friends are sitting in library and working, then I sit in library and work. So the threshold is 40% for going outside and 60% for staying in the library and working. So this value threshold we denote it by a number, let's say Q. So Q is a threshold associated with every node. So at least Q fraction of this node's friends should be convinced, should be adopting a particular decision for this node to adopt the same decision. Now, what was our question? It was related to the clusters. So we have these clusters in this class, and in every cluster there are some nodes, and each node is having some threshold value Q. So here we are assuming that every node is having the same threshold value Q. I'll comment on it later. So every node in every cluster is having this threshold value Q. Now the next important thing, as we know, which needs to be captured is, like we call the density of the community or the amount of unity. So here we define something which is called the density of a cluster. What is the density of a cluster? So, I will give you a one-liner, let us see. So, the density of a cluster is, we say that the density of a cluster is D if you look at every node in this cluster and at least D fraction of this node's friends is in this cluster itself. It might be a bit difficult. Let us look at it with an example. So, let us say that here is this cluster of 5 people. So, there are these 5 people in this cluster, and let us say I say that the density of this cluster is 0.3 if I look at every person in this cluster and 30% of the friends of this person is in this same cluster. So, let us say that in this cluster everybody is having 10 friends. So, I look at this node A, out of these 10 friends 3 should be inside this cluster. For B, out of these 10 friends 3 should be inside this same cluster, and so on for the rest of 3 of the nodes. So, that is what we mean by density of a cluster. So, I hope the definition is clear now. Now, I am going to give you a very weird claim, and the claim says that in this network where the threshold of adoption for every person is Q, as we said before, then the cascade cannot complete itself. Complete itself means starting from some nodes, it cannot sweep the entire network. The cascade cannot complete itself if there exists a cluster in this network of density greater than 1 minus Q. So, how trivial or non-trivial is that? How do we prove it? So, proof is actually very straightforward. Let's look at it with an example that will make it all the more easier. So, for example, what did it say? That threshold for going outside is 40%, threshold for staying in library and studying is 60%. And then in this entire class having different clusters, these are those 2 people who decide that they are going to go outside, and this idea of going outside starts diffusing on this network. Now, assume that there is this cluster of density greater than 1 minus Q. So, Q is here 40%. Cluster of density greater than 1 minus Q means that there is a cluster of density greater than 60%. What does that mean? Cluster of density greater than 60%. It means that if I look at a cluster here and look at every person here, 60% of their friends are in this same cluster. And we know that initially the complete class had actually decided to stay in library and work, and here these 2 people have changed their mind and they said that we are going to go outside. Now, this idea of going outside is diffusing through the network, and let us say while diffusing, this idea comes close to this cluster we are talking about and tries to enter this cluster. Now, see what happens. When this idea tries to enter this cluster, there is this node. So, this node, since it belongs to a cluster of density 1 minus Q, density greater than 1 minus Q, that is density greater than 60%, 60% of his friends are in the same cluster, which means that 60%, more than 60% of its friends have already decided to sit in library and study. So, the threshold condition is not reached. For this node to go outside, the number of its friends going outside, the fraction of its friends going outside and enjoying should be greater than 40%, but that cannot be achieved, right? Because 60% of its friends are already in the same cluster and have decided to stay in library and work. Similarly, this happens for the second node of this cluster, third node of this cluster. So, this cascade is unable to enter inside this cluster, and hence you see our claim is achieved. So, if there is this cluster having density greater than 1 minus Q, no matter what, this cascade which was occurring on this network cannot enter inside this cluster and hence cannot complete itself. Now, I am going to give you another weird statement and let us see how do we prove it. So, the first statement, the first claim which we made here was, if a cascade is diffusing, if an idea is diffusing on a network, and if there is a cluster of density greater than 1 minus q, then the cascade cannot complete itself. Now, what am I going to say? I am going to say that I give you a network and I give you the information about the cascade, and I tell you that the cascade on this network is not complete. There is something which happened inside this network and the cascade couldn't complete itself. There are some nodes which didn't adopt the idea. It means that if this happens, that the cascade is not complete, this implies that, this shows that there is a cluster of density greater than 1 minus q in the network. So, it is a by implication. If you know propositional logic, else just we can leave it aside. So, it is both ways. So, I leave it as an exercise problem to prove it. It is actually very intuitive, like the similar way we did this proof. Okay, let me give you a small hint. So, when this cascade is diffusing on this network and we say that the cascade is not complete, it means that there are some nodes in this network who haven't adopted this idea of going outside. Why didn't they adopt this idea of going outside? Because their threshold was not reached. So, let us represent these set of nodes as set S who didn't adopt your idea. So, these people who are staying in library and studying, we represent them as a set S, and then one by one you examine these person. Why have this node not adopted the idea is because its threshold is not reached. So, using this you can prove this another side of the claim. So, I leave it for you to prove it.